Mayong adlaw o mayong adlaw sa tanan. So here I am again, Sir Junri Anthony M. Remolio from the Department of Agronomy and Plant Breeding. So at this time, I will be discussing the basic principles and concepts of experimental design, which falls under Unit 3 in Agri 44 or Statistics Applied to Agriculture. So in this chapter, you will be aware and introduced of the different terminologies and technical terms related to the introduction of the experimental designs. And you will also be introduced with the different kinds of experiments and when can we use these experiments with respect to the available materials to test, and then we could also consider the available data or particular data of interest that we need to measure. And at the same time, we will also be introduced, or you will also be introduced about what are the different experimental designs. And in the case of the coverage for your midterm exams, you will be until the CRD or the completely randomized design only. So give me a minute to show you my slides in order for me to start with my raw discussion. Okay, okay, here it goes. So it's the basic principles of experimental design. So take note that the concept of the different experimental design applies the appropriate statistic for agricultural research. So there are different terms that we need to define. So first is the scientific method. It is a logical and orderly procedure of investigation. So it involves the formulation and recognition of a problem, as well as the collection of data based on the observation, and at the same time, the formulation of your hypothesis after doing the first two things. Kasi kinahanglan na you have identified a potential and feasible research problem. And that would be the basis on your interest of about what are those interesting traits involved that we need to measure in order to come up with a desired conclusion based on the objectives of solving that particular data or that particular problem. The second one is the research. It is a systematic, controlled, empirical, and critical investigation of hypothetical proposition about the presumed relations among the natural phenomena. From the term itself, research, no, it has a prefix of re and then the root word search. So, in other words, research is a continuous process of validating those data and then verifying whatever conclusions are being formulated. And then the third one is fact. It is the quality of being real and actual, and a truth known by actual observation. In scientific research, no, especially in statistics, we tend to solve some research problems in a systematic way, and we are doing away with such assumptions based on subjective observations, but we are we are more of factual observations that would serve as supporting evidences in order to formulate with a solid conclusion to support and answer the existing research problem. And then the last one is the principle, which refers to a general truth. Of course, before a concept became or becomes a principle, it must start from theories until it becomes a law, and then in turn, a principle. And along the process, there are several, no? Or if not enough, several is not enough, there are numerous researches being conducted in a continuous process of validating such conclusions hand by hand in each process until such time that if there are findings that would solidly support those research problems being answered, then I believe that those laws will become a principle. That is the process, especially as we go along with a research work. Okay, so let's review about the hypothesis. This is a supposition formulated from a proven data and presented as temporary explanation of occurrence in order to establish a basis for further research. So it's very important for us that alongside of formulating your hypothesis, you must have the characteristic of being skeptical despite of the proven data. No? There is a continuous and repetitive investigation, no? In order to really validate, no, if such observation is really factual or it is just by chance. And on the other hand, it is also a preliminary, or hypothesis is a preliminary assumption or tentative explanation that accounts for a set of facts taken to be true for the purpose of investigation and testing, or what we call a theory. And then it is also an assertion or tentative theory which aims to explain facts about the real world. So I believe these are self-explanatory on your part as far as hypothesis is concerned. So there are two types of hypothesis. So the first is the null hypothesis, or the hypothesis of no difference. It is denoted by HO. And then the other one is alternative hypothesis, or the hypothesis of significant difference. And these two hypotheses are of different stands or standpoints. And the rejection of the HO, or the null hypothesis, leads to the acceptance of alternative hypothesis. So at this time, there are four phases that you need to know about an experimental design. So the first one is that in an experimental design, the first phase is about selecting the appropriate materials to test, because identifying those materials that you will use in every research endeavor helps you decide of what appropriate experimental design you need to use, because we will be tackling later what are the different types of experiments. And uh, in order for you to gain information, it could be a path experiment, a laboratory experiment, or a field experiment. Though we could always enumerate different different types of experiment, no, but at least, no, among those diverse kinds or types of experiment, this can be categorized into three major types. So the path, the laboratory, and the field. And they differ with one another, especially with the materials to use, the the characters or the parameters to measure, which is exemplified in the second phase, specifying the characters to measure, because these characters are best measured, no? You can identify if these characters or that particular trait can be best measured in a path, or in a field or in a laboratory. No? You need to remember that there are some particular parameters or characters, especially if you do an undergraduate thesis, no? There are certain characters that are not applicable in the path or in the laboratory or perhaps in the field. And then probably there in the event that there are also some characters that can be measurable in all the experimental or trial types, but at least we can identify that among those types of experiments, which among those can we generate the most valid data, given the actual observation versus the expected observation. And the last one is specifying the difference to determine whether the measurements made support the hypothesis. Of course, the very reason why we do research, why we do experiment is to really identify the differences among those treatments that we impose. And this can be obtained this can be generated once we obtain the results through some different statistical analysis to use. So you will learn all these things extensively as we go along with the topics. And among the four phases, the first two are fairly easy for the subject specialist to specify, while the last two depend heavily on techniques developed by statisticians. Of course, it is imperative for us, or especially for the statistician, to really assess what are the appropriate statistical tools that we need to use with respect to the kind or the type of experiment. And then among the four phases, the last two constitute what is generally termed as design of an experiment. Now, as we all know, there are different types of experimental design. And as much that they are different, they are also subject to application, depending on the applicability or the availability of the materials that you need to test, as well as the characters or the pool of characters that you need to measure. Okay? So you will better understand all these things when you can already experience conducting a thesis or some sort of short-term research. And then we will jump to the three essential components of an experimental design. So first is the experimental error. It refers to the difference among experimental plots treated alike. So it is important for us to learn about an estimate of an error, because whether we like it or not, it would be impossible for us to generate the same results, even with not just with sowing or planting different varieties of crops in two identical plots. And we can also identify some errors even with the same varieties planted in two identical plots. Okay, so for example, if you plant mung bean, say for example, you have two varieties of mung bean, variety A and variety B. And if you plant it on two plots with equal size, side by side, with the same amount of soil, given the same amount of nutrients that you applied through fertilizers, then we can expect differences among those experimental plots. And those differences are very important for us to define estimates of error. And of course, not just for estimate of error, but we also need to learn the control of error, which means or the techniques to minimize the experimental error. That is why in a particular experiment, we do the blocking And then we do the proper plot technique and the data analysis. So in a block, no, we learn that it should be perpendicular to the gradient. No, what I am saying, no, about the gradient, no, is the concentration of the, say for example, the fertility available in the soil. Now, especially if its concentration, no, the degree of the concentration, no, is from highest to lowest concentration, no, going to the right. So and in the event that if you try to assign some treatments, no, in from left to the right, then we could say that there is some sort of bias, especially in the distribution of the nutrients available with respect to whatever assignment or arrangement you did. So that is why in that case we can already identify what are those possible errors that might occur, and that is why we do the blocking, because in the blocking we make sure that we can minimize the errors within block and maximize the errors among blocks. And the very reason why we do randomization is that to provide or to give an equal chance now of all the experimental units of being tested. No? And then aside from the blocking, aside from the proper plot technique, we also do data analysis in such a way that in blocking alone, no, it would be hard for us to really precisely determine if that is really the extent or the degree of the error. And in order to identify such, then we do data analysis. And there are different types of data analysis that we can employ in order to see the different angles of our data, then in turn appreciate those data and coming up with a strong conclusion that would support our research. Okay? And then the last one is the proper interpretation of the results. And that is a very important part, because even though you already have all the data, if you improperly interpret it, because probably you are using a wrong experimental design, or perhaps you are using a wrong statistical tools, then there are errors, and variations that might occur. So that is why we need to do proper interpretation of results. So what are the requirements for having an estimate of error? So first, we need the replication. And it refers to the incorporation of treatments two or more times in an experiment to provide means to measure experimental error. So this can be obtained, no, these are obtained in order to measure an experimental error. Okay? So we need to have replicates of our treatments, no? At least two. And then the second one is the randomization. These are assigning treatments blindly to the experimental units so that each has an equal chance of being assigned to any experimental plot, as what I mentioned earlier. Okay, and there are different kinds of randomization schemes in order for us to do such task or to do such job, which we will learn later on. So these are the randomization skills. You may opt to use the table of random numbers, or you could also do the drawing of cards and then the drawing of lots. Actually, you can do this. No? You can do this, all by yourself, especially the drawing of lots, so as to do the job of randomizing our experimental units to provide an equal chance of being assigned to your experimental plots. So in the table of random numbers, no, I'm not sure if it's here. But usually in the table of random numbers, no, you just close your eyes and then ganyan until such time na kung unsay matunong sa imong tudlo or sa imong pen, no, at the tip of your pen, that would be the starting point, no, wherein you will choose those pool of random numbers and you will assign it to according to the number of experimental units in your experiment. And in a random number, in the pool of random numbers, you are to use the last three digits of those random numbers. So in choosing an experimental design, you need to have the number and the nature of the treatments. And then you also have the objectives of the experiment and the availability of the resources. So it's very important for us to know these things because in a particular study, then the number of treatments will depend on the available resources or the planting materials which would serve as treatments and one of the sources of variation. And there is a corresponding experimental design that you need to use. And of course, our objectives are very important. It must be smart objectives, no? In order for us to achieve the desired results we need to obtain. And the kind of objective, no, whatever objective you have in your experiment corresponds to an appropriate experimental design. Now, say for example, uh, if if you are after the response of the different forage legume species in response to the different abiotic stresses, say for example, if you want to expose it to a drought stress or and waterlogging stress, then since in based on your available resources, no, lahi ang imuhang planting material because different forage legume species. So there is a corresponding experimental design wherein uh, it can precisely measure the differences, the significant differences based on the responses of the different forage legumes rather than the crop species itself. No, kay it is understandable that because lahi gid ang mga crop species, so it is implied nga highly significant gid na sila. And the story is different, no, especially if you also opt to do one crop to be studied with different varieties. So in that way, then you could also obtain a data to be assessed for any significant difference among those varieties with respect to the different treatments that you need to impose. Okay? So there are types of experiments and the basic experimental designs. So there are general types. So first, as what I mentioned earlier, there is that laboratory experiments or trials. And the second one is the path experiments or trials. And the third one is the field experiments or trials. So the first one is the laboratory experiments or trials. This refers to the variance of all or nearly all of the possible influential independent variables not pertinent to the investigation is kept at minimum. And it is done by isolating the research in a physical situation apart from the routine of ordinary living and by manipulating one or more independent variables under rigorously specified, operationalized, and controlled conditions. So in a laboratory experiment, no, in as much that all those investigation is kept at minimum with respect to the independent variables, it simply tells us that doing a laboratory experiment must be in an aseptic and controlled condition. In a laboratory experiment, no, makontrol nimo ang tanang mga factors because usually it is conducted in a laboratory or a specific area wherein there is a constant or fixed room temperature. Okay? So that is all about the laboratory experiment. And there is a corresponding experimental design that is fit to be used in doing such experiment. And then the purposes of laboratory experiment is to discover relations under pure and uncontaminated conditions. In as such that I've mentioned earlier nga, you can control the different factors in order to come up with a pure culture, or say for example in a plant pathology, no? So kung buhat kag laboratory experiment, no, under or simply in a laboratory experiment, no, you can manipulate or control the environmental factor that might be a potential factor to cause variation in your experimental units. And then the second one is to test predictions derived from theory primarily and other research secondarily. And then it is also purposely done to refine theories and hypotheses, especially if there are already conducted researches in the past, and if you want to validate the result, then you could do laboratory experiment, especially that if you try to compare such study in a field setting or in a field condition and in the laboratory condition. And then the purpose also is to formulate hypotheses related to other experimentally tested hypotheses. So out of those formulated suppositions, then conducting such experiment, no, I'm referring to the laboratory experiment, would prove or disprove the validity of such result. Okay, what are the strengths of the laboratory experiments? So there is a possibility of relatively complete control. I've already mentioned that earlier because in a laboratory experiment, it is designed to purposely eliminate many extraneous influences that may affect the dependent variable, especially when you do the study when you compare it to a field experiment. No, remember that there is a so-called formula in plant breeding or in crop improvement wherein P, which stands for phenotype, that refers to the physical appearance of a particular crop, and we could also say that that would also pertain to the desired outcome that you need to obtain. So P is equals to G, which means to the genetics, times the E or the environmental factor, and then I'm sorry, no, not times, plus. So P is equals G or the genetic factor plus E, the environmental factor plus the interaction between the G and E or G by E. So G times the genetic times environment. So we need to consider all those factors because these are potential factors that would cause variation or extraneous influence. And then another strength is achieving high degree of specificity of the variable. And then it also has a high precision and replicability in as much that it is being conducted under aseptic condition. So that is all about the laboratory experiment. And then the second one is the pot experiment or trial. Of course, from the term itself, pot experiment, then placing pots with the desired amount of soil samples and under conditions that may be controlled to some extent. And its purpose is to provide rapid means of screening experimental materials such as soil for potential nutritional limitations. Because if you are dealing with soil condition, then it is much convenient to adapt pot experiment because you will only need a, a small amount of soil compared to the field. And of course, no, if you do it in an aseptic condition, then you need to sterilize it through heating. So I believe that pot experiment would be much convenient for a researcher to conduct its study. And then it is also to estimate the approximate rates of materials as fertilizers needed. And the pot may contain the exact volume of the soil needed by the plant throughout its growing period. And the volume of rhizosphere should be bigger if yield data is desired. However, no, and it will be mentioned, no, later on in the disadvantages, no, or the limitation, no, we could actually harvest our crops, no, or we could come up with an immature data as far as doing pot experiment is concerned, because compared to the field, the area compared to the field is much larger than in the pot. Although if you want to validate such data and you want to do it in aseptic condition or in controlled condition, pot experiment could also be effective. Okay? The advantages of pot trials over field trials, no, it requires less time and materials. And then it can be used to test several treatments, and then it can provide diagnostic result more quickly. Of course, you need to set a particular stage of the crop, wherein that would be the terminal stage in the pot, because as we all know, the pot itself is a limiting factor in order for you to study the whole plant or the entire plant. Okay, and that would tantamount to the limitations of the pot, because pot trials may sometimes identify disorders which do not occur in the field or vice versa, because water or other climatic factors limit plant growth in the field, and the amount of nutrients available to the plant may differ between the pot and the field. No, if you try to compare the difference between the area in the field and then in the pot experiment, okay, in terms of if we consider the factors, the environmental factors, no, there is a huge difference between the two types of experiment. And then the indicator plant or the test plant in pot trials is usually harvested at an immature stage. So in my case, no, I have an experience that in one of my short-term research and even in my undergraduate thesis, then I did pot experiment, and usually I already terminate all my crops, no, at the seedling stage or in the early vegetative stage. So things like that. That is the context of harvesting in an immature stage. Whereas if you do it in the field experiment, you could do a morpho or agronomic characterization or assessment of those crops, because you can obtain some data, no, related to the yield and its yield components, things like that. Okay, and the third one, field experiments or trials. So it is a study in a realistic situation, because from the word itself, realistic, no, because the habitat or the nature of our plants are usually belong to the field. So the study in a realistic situation where the interplay of plant, soil, and management practices and environmental factors can occur. And study in a realistic situation in which one or more independent variables are manipulated by the researcher under as carefully controlled conditions as the situation will permit. Okay? So, this is what we call that our only option is just to prepare or to provide a favorable environment for our experimental units because uh, the condition or the situation of that particular area would depend on the kind of weather, no, or what are the herbivores or herbivores that are present in such field, and we cannot control that, no, although we could apply pesticides, no, or other methods that we need to apply. But the idea there is that when we talk about the situation permits, so it totally depends on the kind of environment where you will establish your experiment. And that is the nature of a field experiment. And the only way to establish fertilizer requirement accurately is by means of field experiments where the full interplay of plant, soil management, environmental factors can occur. And the last one, the assessment of soil homogeneity for field experiments is necessary, especially for soil pH mapping, soil fertility gradient. So these things can only be done or can only be possible to be assessed under field experiment. Okay? Because when you compare it to a pot experiment, no, it is just a parcel of land, no? Or a representative area of the soil in a particular land that you will collect and use as medium for your pot experiment. Things like that. And then the advantages of field experiment, it is the ultimate basis in making decisions as that of the fertilizer recommendation. Because whether we like it or not, no, if we talk about sustainability, no, so as to assess the performance of our of our crops, then we could come up with a valid data, no, if we expose our experimental plants, no, or experimental units in the field trials. No, remember that there are most of the seed companies do field demo or trials in different locations of particular place, no, say for example in Mindanao, they will do multi-location trials in order to assess the performance of their planting materials. And then results can be extrapolated or transferred to other areas with similar situations. And then it show the benefits of the treatments to the farmers. And then economic evaluation of the results will give a better insight. Okay? And we can only obtain such factors, no, or such aspects when we do field experiment. No, ang atong farmers, they do their farming in the field. So they may be experts, no, when you solicit comments or observations on the field based on their activities. Okay? And then the limitations of the field trials, it is time consuming. No? We are all aware of that. It requires more effort in the assessment. It requires large input of materials and limited number of treatments can be tested. No? Sa tubig palang daan, no? The liters of water that we will use when you compare field and pot experiment, no? Dako kayo ang difference. That is what large input means, no? water, that is just for water alone. How about for the fertilizers and other inputs, farm inputs that you need to apply, no? And then given the fact that in the field it is prone to nutrient leaching because you apply it in the soil, in the field, things like that. Okay, so we will just have a recap or an overview, rather, overview of the different kinds of experiments based on the factors involved. So there is what we call single factor, wherein from the word itself single, so it is only one factor that varies while others are kept constant. So dili na may mong single if more than one, no? So the different experimental design under single factor experiments are simple CRD or the completely randomized design, the simple RCBD or the random complete block design, and then the Latin square design. And for the multiple factor experiments, there are two or more factors vary and others are held constant. So the split plot, the strip plot, the split plot, the split plot, no, parang tongue twister, no? And then the factorial in CRD and factorial in RCBD. Okay? So we will tackle all these things successively as we go deeper in the basics of experimental design. So here we go, no? Our first basic experimental design would be the completely randomized design, or what we call CRD. Okay? What is CRD? It is an experimental design whereby treatments are assigned entirely at random. No? Random in terms of the treatments and the replication. So they are entirely random and enjoined, no? When you base it in the layout. So randomization is made in such a way that each experimental unit has the same opportunity to receive any of the treatments. And any difference between EUs or experimental units receiving the same treatment is considered an experimental error. So that is why it is only appropriate for experiments with homogeneous experimental units, particularly the laboratory experiments and controlled and small experiments. So with that statement alone, you need to remember what would be the appropriate design when you conduct laboratory experiments. Okay? And as such that in a laboratory experiment, no, controlled tanan, almost identical tanan, so the most appropriate design would be CRD. But it would also depend, no? Depende sa nature sa imuhang experiment or sa imong study, then you could also switch to simple RCBD. So it would totally depend on the location, the condition, or the kind of area that wherein you will place your experimental units. So things like that. And the features of CRD, it is simple. It is simple and easy to compute, which I will show later how to compute. And then the feasibility, it is feasible because the number of treatments and replications are not limited by the experimental design, but only by the experimental units available. Okay. Naku, mapagaw. Okay, for the randomization layout, the randomization and layout of a CRD involve a step-by-step procedure. So in an experiment with T treatments and R replications per treatment, then there are N experimental units. Okay, so given, for example, I know you're already familiar with it during your CPSci 41A. So in your exercise number 3, you say for example you were given 5 treatments, and you replicate it 3 times, so that corresponds to your R and T, and which result the product would be the total experimental units. So 5 times 3 equals 15. Okay? And then the randomization is done by using any of the randomization schemes. So as what I mentioned earlier, you could do the table of random numbers. No, Morabag, say for example, these are the pool. Let me show you, ha. Okay. So for example, no, assuming these are the random numbers, so piyong lang din ka, and then, okay? So kung matunong, that would be the starting point. And then, as such that this is a starting point, you assign, no, based on the pool of numbers, no, the pool of numbers, random numbers, then you assign your experimental units. And then you will use the last 3 digits of each random numbers as basis for your ranking. And that would be your reference on how you will assign your experimental units, no, in a particular layout. And with that, you are already doing the randomization. Okay? Or you could also do the drawing lots, no? Drawing lots, or you could also do the use of cards, no? And you could also use your calculator. I believe that you were already taught how to do randomization using your calculator. But in the calculator, you are only using the last 2 digits. Since the digits, no, or the denominations or the digits of the random numbers in your calculator are only 3, I think. Let me check. Oh, 4, but it's in a decimal form. Things like that. And then, say for example, no, for an experiment of 5 treatments, so these are the examples of CRD, no. There are 9 ka-treatment and there are 4 replicates. So how many experimental units? So you just multiply your treatments and your replicates. And the product would be 20. And that would serve as your N, or your number of experimental units. And after which, you randomize the 5 treatments in 4 replicates into 20 experimental units using any of the randomization schemes. Okay? So this is the example, no, based on the slide. This is the table of random numbers. So katong gihon nga mo piyong mo, and then itudlo lang niyo using any object that has a pointed, no, tip or edge. Then kung unsang number ang matunong, that would be your starting point. So say for example, based on the slide, you will start at 0.6769. So this would be the number that you will assign to your first experimental unit, and you need to assign random numbers, no, successively, no, until such time that you will assign all your 20 experimental units. Okay? So mamili lang mo ani, ha. You don't need to do cards, no, or drawing of lots, no, just to satisfy the randomization. Mamili lang ka. Okay? And then you rank the n random numbers obtained in ascending or descending order. And you already assign the corresponding random numbers. So in this case, ang gigamit is the last 3 digits. So makita ninyo, no, as you assign random numbers to your experimental units, no, then you will be able to rank them. So of course, ang pinakauna, ang number 1, katong pinakagamay. Then, until nga, ma-rank ni siya in increasing order until moabot ta, maka-assign ta sa 20th experimental unit. Okay? And then you divide the n ranks into t groups, each consisting of r numbers according to the sequence in which these numbers appeared. Okay, let's continue. And then, no, after nimo ma-assign, and then you need to group them. You group your experimental units, no, based on the treatments, no, or yeah, based on the treatments, and then ang tapa din na niya, no, you will input, no, what is the rank, no, based on the assigned random number. So makita nimo, no, all the treatments, no, since there are four, I think there are 4 replications. So in treatment A, no, for example, in treatment A, since there are 4 replications, no, so each replication were assigned a different random number, and that would serve as the rank. And sa B po dayon, sa C, sa D, and sa E. Okay? I think masabtan na siya. So this would be your possible layout of an experiment with 5 treatments and 4 replicates. So that is in the case of CRD, because in CRD, no, based on the features of CRD, you are actually randomizing, no, both the treatments and the replications in one layout. So technically, wala pa na block diha, because we will be able to use blocks when we discuss about RCBD, pero dili pa ni siya appeal sa midterms. Okay? You could also do the drawing of cards if you like. So you could just determine the total number of n of the experimental units. Then from a deck of 52 cards, draw n cards one at a time, mixing the remaining cards after each draw. But the only limitation about a randomization scheme using drawing of cards, so 52 lang ka card, ang 52 lang ka experimental units ang capacity. So if you have more than 52 experimental units, then drawing of cards, no, is not applicable. This random scheme is not applicable. Okay? So this would be the sample table for the analysis of variance or the Anova for CRD. So as you can see in the table, we could have 3 sources of variation. So the treatment, the error, and the total. And the second column is the DF, or the degrees of freedom. Okay? And in order to compute for the treatment DF, then we need to get the difference between the number of treatments minus 1, as shown below the table. And for the total DF, we need to get the difference between the total number of n, or the experimental units, minus 1. And for the error DF, you need to get the difference between the total DF and the treatment DF. Okay? Then, and the third column is the sum of squares. So you need to get the value of the treatment sum of squares, no? And then the error SS, and then the TSS. And then the fourth column is the mean square, no? And then you need to get the mean square for the treatment and for the error, and we will also compute for the computation of the FComp. Okay? And then in order to obtain such value, then we need to get the quotient between your mean of square treatment mean of square rather, and the error mean of square. Okay? So I hope you could follow. And then for the F tab, the value of F tab can be found in the appendix E, which I will also show in the slides. So this will be helpful for you in obtaining such values, no, of distribution of F. Okay? So it depends on the number of your treatment error, no, and then your treatment, kumbaga treatment DF and the error DF. Okay? So, these are the pool of formulas. So, you love formulas, right? So, CF stands for the correction factor. And in order to obtain such, then we need to get the square. You need to get the quotient between, or you need to divide no the square of the summation of x, or the sum total, and x corresponds to the values of the observations divided by n, or the total number of observations. And for total SS, or the TSS, which means the treatment total, then the formula is summation x squared minus correction factor. And then for the TRSS, or treatment sum of squares, then you need to get the difference of the difference between the quotient of the summation of treatment squared over the replication, and the difference between that og sa inyong correction factor. And for the treatment SS, there are two formulas in getting for the treatment sum of squares. So the first one, which I introduced, is applicable for treatments with equal number of replicates. But however, if there are treatments with an equal number of replicates, then you opt to use the second formula. Don't worry, I will show you later, sample problems with treatments with equal replications and unequal replications. And then for the error SS, you need to get the difference between the total SS and your treatment SS. Okay, and then same, you just go over with the formula in getting for the treatment mean of square and for the error mean of square and the M computation. But the F value should only be computed only when error DF is large enough for a reliable estimate of error variance. That is, when the error DF is greater than or equal to 6. Okay? If mo compute kasi mong error DF, kung greater than or equal to 6, then compute na sa itong F value. Okay? So these are the decisions. If the F computation value is greater than or equal than the F tab value at 1% level of significance, then the treatment difference is highly significant, which is designated by double asterisk. Okay? However, on the other hand, if the F computation value is greater than or equal than the F tab at 5% level of significance, but lesser than the F tab at 1% level, then the treatment difference is significant, designated by 1 asterisk. And then the last one, if the F computation value is lesser than the F tab value at 5% level of significance, then the treatment difference is non-significant, designated by NS. So which means that if your treatments based on the analysis as per Anova, if mag-NS gina siya, it means that particular treatment is comparable with your control, which would serve as the treatment, the ideal treatment wherein you impose the ideal growth and development of your crop, especially in cases that you are to evaluate the normal growth and development of your crop. And when you compare it, if you try to impose some treatments, say for example, if you want to assess the growth and development of your crops in response to the different abiotic stresses, say for example at the seedling stage, things like that, then you are trying to compare that if there are differences. And that is actually a good data if you would come up with highly significant and significant. And speaking of NS, no, it is also a good data because it means that especially if that particular treatment, no, if that particular treatment is non-significant no compared to control, it means that especially if that treatment no is barato lang, easy to formulate, no, then it gives us a hint no nga mas pareha ra day ang ilang performance if we compare it with the control. Especially no if your control no diya nimo ginabutang ang conventional and ideal nga treatment nga imong i-impose sa imong practice. Okay? So another pool of formulas in order to get the coefficient of variation. First, no, as we estimate for the errors, then there is also that variation that would be accumulated now as we go along with the analysis of our data. And these are very relevant and a determining factor no that would reveal if naabay mga discrepancy sa inyong methodology. It's telling enough that if there are some problems with your methodology that causes variation. Okay, and then for the standard error and for the standard difference of the treatment mean, no, there are two different formulas, no. There's a formula with equal number of replicates, and then for treatments with unequal number of replicates. Okay? For example, no, nanata sa example. So, the dry matter yields, no, which is in units gram per pot of corn as affected by the organic fertilizers at 30 days after planting. Okay? As you can observe in the formula, you can see that there is an equal replication since all the treatments have 4 replications. So technically, no, it has 4 replications. So you can say that equal ang iyang replication. So there is a corresponding total no for the treatments. So in order for us to perform the Anova, then we need to compute the important values using the formulas that I showed earlier. So you need to compute for the treatment DF. So applying the formula T minus 1, since there are 5 treatments, so minus 1 equals 4. For total DF, N minus 1. So going back to the table, no, as you can see, since there are 5 treatments and 4 replications, so if you multiply 5 by 4, that would correspond to your value of N, or the total number of experimental units. So that is why the value of N is 20. So in order to obtain the value of your total DF, then 20 minus 1 equals 19. Okay? And for your error DF, you need to obtain the difference between your total DF and your treatment DF. So 19 minus 4 equals 15. Okay? So kindly jot down all these numbers, no? Or these values if you also try to solve it on your own. So going back to the table. So of course, we also need to obtain the value of your total sum of squares and your treatment sum of squares. And based on the formula, no, in order for us to obtain the total sum of squares, so we need to get the value of your summation of x squared. And in order for you to obtain the value of your summation x squared, then you need to get the sum of the squares of this value from 29.2 up to the 59. So in short, no, tanang value, tanang 20 experimental units, you need to get the square of each experimental units, then you get the sum. So that is for your TSS. And in order for you to get the treatment sum of squares, then you also obtain the value through the treatment, the total treatments. So makita ninyo diya, no? So with this idea, then we can come up with an insight on how to compute how to compute for our total SS and our TRSS, and how we can incorporate the values using the formula provided. So actually it's a very long process of computation, but uh, this is how we can compute uh, for the different values. So actually, I didn't I didn't didn't round it off, no, tanang mga values dire kay kung dili pa nimo na siya i-round off, no, there is a possibility nga makakuha tag value nga less ang iyahang variation or iyang error. So mo na nga, if you do the rounding off, no, that is just for presentation purposes na lang. But before ka mag-round off gyud sa final value, then sa imong pag-compute sa mga value niya, ayaw sa i-round off. Gamiton sa nimo ang iyahang raw value. Tip lang na siya, no? That is just a tip. Okay? So ayaw mo pagdiretso round off because huge na kayo ang difference sa values kung mag-round off ka daan. That is why, as you can see, no, there are some values there nga taas pa kay decimal point. But in the Anova table, that is the time nga dito na ko nag-round off. Based na kung nahuman na nimo tanan compute tanan. Okay? So for your correction factor, applying deriving the formula using the values in the table. So the total summation of x is 858.8. So you just get the square of the value divided by 20, which is the total number of n. Then it will result to 36,876.87. And for the total SS, you need to get the value of your summation of x squared and minus the correction factor. So going back to the table, makita ninyo ang value ang value ang summation x squared which is from the total value of the squared value of the experimental units mao ni siya ang iyang value niya 39,633.2. And after obtaining the value of your summation x squared, deduct nimo sa correction factor. So that would be the result, 2,756.32. Okay? As well as for your TRSS, no? The value of the sum, no? The sum of the squares of your treatment, no? Kaning violet. So ang value niya is kaning 157,643.32 divided by 4, which represents the total number of replications. It will result to 39,410.83 minus the correction factor. It will result to 2,533.96. Okay? And same process no as you compute for the ESS, it will result to 222.36 for your treatment MS, 633.49, and then for your error mean of square, 14.82, and for your FCOM, 42.73. I hope you could follow and be able to derive all the values using the formula given. And then, this would be the final result. Based on our computations, we could come up with the values, no, in the ANOVA table. Okay? So, as you can see, the F computation value is 42.73, and it is highly significant because we base it on a decision making, no, nga if the value of the F comp is greater than or equal than the 1% level na F tab or 0.01, so we could decide that it is highly significant. Okay? Mangutana mo, where did we obtain that the value of 3.06 and 4.89? So you can actually obtain the values, no, in your table, no, which I already attached in this slide. So as you can see, no, we base it on the treatment DF, which is 4, and the error DF, no, which is 15. So for the column part, no, we will base it with the treatment DF, and for the error DF, ang row part. So since ang treatment DF is 4, I don't know if makuha ninyo ni Pro, ingan nyo na lang, imagine na lang. So there are numbers from 1 to 500, and then the treatment DF is 4, and the error DF is 15. So it falls on the second page. So makita nato diri, no, kung tanaw nato, no, ang value between treatment DF and the error DF, no, we could come up with the value of 3.06 and 4.89. So the light value, or should we say the light type, corresponds to your 5%, no, or 0.05, whereas ang kaning bold type mo na siya ang 1% or 0.01. So going back to our computed F computation, since mas dako man siya sa inyong 1% level, no, level of significance, so we could decide that it is highly significant. Okay? So that is all about the equal replication. And then we could now jump to the CRD with unequal replication. So last na lang yun, no? What lang yun? Kanang pugong lang ta, no? So remember that for CRD with unequal replications, remember that in getting for the standard difference for the treatment means, as well as for getting the treatment sum of squares, then there are two different formulas, and these are the two formulas that are applicable for unequal replications. Okay? So, going back to our example, however, the only difference is that naay mga missing nga data. So which means that there is an unequal replication, especially, no, ang affected nga treatment is ang treatment 2 ug ang treatment 5. Okay? So how can we compute, no? Same ra gyapon nga manner sa inyong computation. No, however, pag abot sa inyong treatment SS o sa inyong standard difference of the treatment means, you will use the appropriate formula that are applicable for unequal replications. Okay? So again, you will compute for your treatment DF, for the total DF, and for the error DF. So I think for the treatment DF, there are no changes. However, for the total DF o sa inyong error DF, nanay changes because nabago na atong value sa atong n. Instead of 20 in the first example, nahimo na siyang 18. Okay? There are two missing experimental units, no? So unequal na siya. So minus 1 equals 17. And maapektuhan na po din inyong error DF because na-change man ang inyong total DF. So the error DF would be 13. And this would be our new basis, no? Kung mo mangita na tag value for our 5% and our 1% level of significance. Okay? So, you just incorporate the same formula. Amo na'y bahala na, no? But I will just explain for that treatment SS on how we can obtain the value. So, you just have to compute, no, isa-isahon nimo og kuha, no, ang quotient, no, of the different experimental units, because as you can see, no, the formula is T1 squared over R1. Kay there are some instances, no, nga ang treatment, no, there is a treatment, specific treatment nga dili equal ang iyahang number of replication. So say for example, if we go back to the table, no, if we obtain that treatment as a, so normally, no, in the equal replication, diretso na nato siya makuha kay pareha man sa tanan. But in the case of unequal replication, then we need to, this would be our mathematical sentence, no? As we derive the formula, 106.3 squared over 4, since treatment 1 does 4 replications, plus 145.5 over a square over 3, plus 196 divided by 196 squared over 4, plus 135.7 squared over 4, plus 173.5 over 3. So with that, naka-obtain na to ang iyang value sa 34,123.37 minus the correction factor, which results to 2,287.32. And same process goes to our other formulas and values that we need to compute. So, this would be our Anova table for our example number 2 with unequal replications. Okay? So, when you incorporate the value of your sum of squares for the treatment and error and total, as well as the mean squares for your treatment and error, then we could come up with the decision making, no? And as you can see, highly significant gyapon siya. And where did we obtain the value 3.18 for the 5% level of significance and the 5.20 for the 1% significance? So, balik na po din ta sa table. Okay, I think I already attached the table near this slide. So, since our treatment DF is 4 and our treatment DF is 13, then this will be our basis, no, in plotting for the value. So, as what I mentioned earlier, ang basis for our column, no, kay ang treatment, and for the rows kay ang error. So if we try to plot, no, using this table, so makita nato, no, in the column part ang 4, no, makita nato ang 4, and then since the error DF is 13, so we could come up with a value of 318 for 5% and then 5.24 for 1%. Okay? So these are the important table that you need to grab or you need to have in order to answer the questions related to Anova in CRD. Okay? So I think that is all of my presentation as far as experimental design in CRD is concerned. Okay, so I will try to stop sharing my slides. So, if you have questions related to this topic, then feel free to contact me through your leaders. And for those students who find this topic interesting, then feel free to contact me through my email address provided, no, in my YouTube channel. So, thank you very much for listening, and I hope nga dagan mo og nasabtan. So, keep posted for more videos which I will upload in your Google Classroom. So thank you very much and goodbye for now.